Hello guys, so this is the video editorial for Beautiful Subsequence in July Cook-Off. So we'll start with a brief introduction. So I am Istasis Mishra. I'm a fourth year undergraduate at IIIT Hyderabad right now, currently pursuing a dual degree BTech and MS in computer science engineering by research. So I got into this university because I represented India in IY 2018, and after that I have been to ICPC regionals twice in my first and second year. So I have been an unacademy educator since March. So I think that does as an introduction, and we should just start. So this is the problem, right? So yeah, you're given an array A of n integers that is called k beautiful if it holds the following property. The number of adjacent indices with different values is at most k. So what does that mean? K beautiful, right? This is the definition that we need to understand. So k beautiful, let's say k equals 2. So that means an array 2 1. So you can see this is one time when the adjacent numbers are not equal. This is one time the adjacent numbers are not equal. So how many times does that happen? 2 times, right? So this array is too beautiful. But if that happened more than, so let's say 2 2 1 2, something like this. In this case, this is one in one time, this is one time, this is one time. 3 times it happens, right? So this is not too beautiful, right? And the definition says that the number of times the adjacent numbers are adjacent integers are different, it should be at most k, right? So this here it's 0, right? The number of times the adjacent numbers are different, it's 0, but still this is this is too beautiful. This is still too beautiful. Why? Because the number of times the adjacent integers are different is at most 2, right? So let's go back to the problem. So let's assume that we now understand what being k beautiful means, right? The number of adjacent integers with different indices with different values is at most k, right? At most is a important part, right? So more formally, so ai is not equal to ai plus 1, right? Yeah, so this is the important part. Note that according to this definition, if an array A is k beautiful, then A is also k plus 1 beautiful. So if an array is already 2 beautiful, that means it's also 3 beautiful. That means it's also 4 beautiful, and so on, right? So yeah, now this is the problem statement. You are given an array A with n integers and also an integer k. You have to find the length of the longest k beautiful subsequence of A. What is a subsequence? Subsequence. So let's assume this is our array 1 2 3 8 4 6, right? So a subsequence of this can be 1 3 8, right? It can be 3 4, right? Any integer we can take like a subset, but it should be in order as it is given in the array, right? So that is the difference between a subset and a subsequence. So going back to the problem, so we have to find we are given array of n integers and k. We have to find the length of the longest k beautiful subsequence. Okay. So we also have t number of test cases. So yeah, 100 test cases, we n is up to 10 power 3, k is up to 10 power 3. AI is up to 10 power 3, right? So these are a few examples. Let's, work them out. Okay. In our first example, our array looks something like 1 1 2 3. 1 1 2 3. Okay. And our k is 1. K equals 1. So what is the length of the largest one beautiful subsequence? So 1 1 2, right? This is fine. So our answer will be 3. So our second test case is something like 1 2 3 2 4 5 6 7 5. 1 2 3 2 4 5 6 7 5, and k is equal to 2. Okay, so what subsequence do you think will be the longest? Think it should be 1 2 2 5 5, right? So the answer will be 5. So 1 2 2 5 5. In this order, if you look at it, how many times do the adjacent elements differ? 2 times, right? So this is a 2 beautiful subsequence, and this is the longest you can find. So you can try to find longer, but you will not be able to find it. You can try it. So the answer is 5. Let's look at more. So 5 5 5 5 5, and k is equal to 5. So what is the answer? The answer is 5. The whole array we can take, right? All of them are equal. So this is a 0 beautiful array, right? A 0 beautiful array is also a 1 beautiful array. A 1 beautiful array is a 2 beautiful array, and so on. We can say that this is also a 5 beautiful array. So hopefully we understand what the problem is asking for now. Can try to solve it. We can think something kind of greedy, right? We can think of a greedy solution here. It seems like taking the element with the highest frequency or something like that should be better, but the problem is none of it works. So this is actually a dynamic programming problem. Okay, so in a dynamic programming problem, what we do is we define a function, we give it some states that we want. So here I and k are called my states, right? So states are my I and k. So I now need to define what fik means, right? So let me erase this. So yeah, fik means longest k beautiful array if we consider first I elements. Okay, so as an example, if 1 2 2 3 4 4 is our the thing, so f of 2 1 will be equal to what? So 0 1 2. So in the first I elements, what is the longest one beautiful subsequence? It's one what is the length of the longest one beautiful subsequence, right? So it's 3, right? So hopefully this makes sense. And yeah, there is an additional thing. First I elements ending with AI, right? It should end in AI. Okay. So this is something that I personally call the informal definition of our recursive function, right? So f is supposed to be a recursive function. If we have a dynamic programming solution, f is supposed to be a recursive function. Okay. So if f is a recursive function, then it must have a recursive definition. But what does f of ik even mean in English? So that I called an informal definition. The recursive function is what I call a formal definition. Okay. So if you look at the editorial kind of gives it as max of j less than I f of j comma k dash plus 1. Okay. We will see what this means. Okay. And k dash is equal to k if ai equal to aj or k minus 1 otherwise. Okay. So what does this mean? So for every j less than I, we are making j the second last element. So if j is the second last element, so if ai and aj are equal, right, and we want our subsequence to end at ai, and we want it to be k beautiful. So till aj, it must be also k beautiful, because we are adding one element and ai and aj are equal. So let's say aj is 2, and before that there are some elements, and beech mein there are some elements, and then this is my aj and this is my ai is also 2, right? ai. So aj is my second last element in the subsequence that I want to take, and ai is the last element, right? So if till here this is k beautiful, then till here it is also k beautiful, right? So that is why we take fjk plus 1. For why plus 1? Because we are adding ai to that subsequence, right? So we are increasing the size by 1. Okay. So if it is equal, then we till aj it must be k beautiful, and till ai also it is k beautiful. Now if you want till ai to be k beautiful, and this is, let's say, something like 3, so till aj it must be k minus 1 beautiful, because if till aj it's k minus 1 beautiful and then we add 2, it must be k beautiful then, right? So that is why we have this k dash, which means k if ai is equal to aj or k minus 1 otherwise. Okay. So I hope this is understandable. You can pause here, take some time to understand what this means. I've already explained. You can go back and see the video as well. So what is the complexity of this solution, right? What are the number of states? This can have n different values. This can have capital K number of values, right? And each of these will take O of n time to calculate, right? Because we have to see all the j less than I. So overall our complexity becomes n square k, right? But we know that n and k both can go up to 1000. So this will not pass. This is 10 power 9, right? So what do we do? We can see that we have two things here, right? What if we separate the two? Let's assume, let's think about all the aj's that are not equal to ai, right? All the ages that are not equal to ai, we only need max among all of them, right? So we define a pref max. pref max of ij, yeah, ik will be equal to max j less than I or f of jk, right? So this value for everything, for every aj that is not equal, right? If it's equal, it's k beautiful, right? Otherwise it will be k plus 1 beautiful. But something that is already k beautiful is k plus 1 beautiful, right? So we don't have a problem here. So pref max ik, I will come to what I just said again. Okay? If you did not understand what I just said, we'll come back to it. Okay? So pref max ik is till I all the maximum. So k is constant. So what is this? It will be pref max till I minus 1k, and so it will be max of the two, right? Max of pref max till I minus 1. Sorry, no, I minus 2 till I. F of I minus 1, okay, right? So f of I minus 1k and pref max of I minus 2k, if you take the max of both, that will be pref max of, so prefix max, that is what it means. So prefix max of fik, k will be the constant. So why is this important? Because for every aj that is not equal, we have to take what? So now fik will be equal max of two things, right? So I'll write it in two lines. So here we will have the case when for every aj that is equal to ai, for all aj equal to ai, right? And second one is for all aj not equal to ai. So if they're not equal, then we only have to take the maximum, right? Maximum of all of them and plus 1, right? Max of everything plus 1, right? So that is given by pref max. So assume, so make it equal, okay? Let's make it equal because that is how the editorial also does it. So this will be I minus 1 and this will be I, right? So this will be given by pref max of I minus 1k, k minus 1, right? Till I minus 1, I want the maximum k minus 1 beautiful subsequence, since aj is not equal to ai, right? You will notice that in some cases it will actually be equal, and if it's equal, it's now k minus 1 beautiful, right? But a subsequence that is k minus 1 beautiful is also k beautiful, so that is also covered here, right? Now in this case we can see aj is equal to ai. This begs a question. Let's say our ai is equal to 2 and there are a few 2's before and 2, so this is our ai, right? So this is one possible aj, this is one possible aj, this is one possible aj, and so on, right? Do we have to consider all of them? No, right? Because if till here we get the longest so it's kind of greedy in a sense, right? If till here we have the longest k beautiful subsequence, we can just extend it by adding this, right? And it will still be k beautiful, right? So we are only adding one, so iske baad ye nahi aa sakta. So but from this you cannot come to this. These two 2's must be taken into account, right? This cannot be the second last element. The last occurrence of 2 has to be the second last element. Is that understandable? Because if the last occurrence of 2 is not the last element, second last element, then I can make it the second last element by just adding it, right? If this is the second last element and then I come here, I could have had something longer by putting this 2 in between, right? So that is the reason we only need the last occurrence. So for every element, we also save last AI. So last AI is what is the last occurrence of AI. So for that, I'll have f of last of AI. Okay, right? So I'll have max between the two. So I can erase this. Max between the two plus 1 and I'm done, right? And now this is O of 1 calculation, this prefix max. So after I calculate Fik, I have to update prefix max. I have to update prefix max. I also have to update last AI. Both of these are O of 1 operations. This max is also an O of 1 operation. So you can see for each state, now instead of doing O of n operation, I'm doing O of 1 operations, right? So what is the complexity now? The overall complexity comes out to be O of nk, right? Which is 10 power 6. And we have 100 test cases, so that will come to 10 power 8. So this will pass. So this is the final solution. So the editorial, so let me come back to the thing. So the editorial uses the exact same notation. So after seeing this video, you can also look at the editorial. You can see this is the case. So 1 plus max of pref I minus 1 k minus 1 and last of ik, right? So this is for not equal, this is for equal, right? There is also a slightly different approach that I'm not going to talk about in this video, right? So talking about implementation, okay? So let's take the setters implementation and just a second. So yeah, this is the code, right? Very small, not very difficult. So the solve function is the main thing that we are interested in, right? Input, this is all input. So this is, right? So this is our DP, DP of nk. So this is our f function, the memoized DP array of the f function, right? This is the last IDX, the last I, and this is the max. So this is the pref max, right? So maximum answer till yeah. So yeah, dpij okay. Yeah, so dpij, if j is greater than equals to 1, we first take max of j minus 1 plus 1, right? And if last, so initially it's all minus 1, right? So if last IDX of AI is minus 1, that means AI has not been visited before. Like there is no previous occurrence of AI. So that is why it's minus 1. So if it's minus 1, we don't do anything, right? We are done. It's just max answer j minus 1 plus 1. Okay. Otherwise, dpij will be max of that plus this j is the k, right? This j is still there. J will be stay j. Here it's j minus 1, And so this mx answer, our pref max was what? It was ik, right? So change that to ij, and then since we only need I minus 1, we don't need to save the whole 2D array, right? We can only save the last, the previous layer. So that is why it's a 1D array, not a 2D array. Okay. So dp last index of ai, j plus 1. So these two lines are taking the max of the two things. Now we have to update our mx answer. Mx answer j will be max dpij. That is it. And our answer, answer is this max of. So after calculating all the dps, answer is the max among all the dpijs, right? And finally, once we are done with this j, we the current j, after we are done with it, we just take our last, we just update the last index of ai to I, right? Because then we'll go to I plus 1, and finally just print the answer. So to reiterate, this is just the input, right? All of these, this just input. This is initialization of the arrays. dp is our memoized f function. Last index is the last function we talked about, and mx answer is that our prefix max. Okay, this is a 1D array instead of a 2D array, because we don't need like I minus 2th layer. We don't need. We only need the I minus 1 part, right? So that is why it's a 1D array. We don't need to save everything. We can, but we don't need to. Okay, so these two are taking the max of the two different cases, right? If j is not greater than equals to 1, this max answer does not exist, right? So we do not need to take it. So this is one condition that we have to check. This is also another condition to check if ai has occurred before. If ai has not occurred before, we do not need to do this update, right? And finally, after calculating our dpij, we have to update these two. Max answer of j will be max of whatever j max we have taken till now, and dpij also. Like we have to take the max of all of them. And our answer is just, so we are updating our answer as among all dpijs, this is our max, right? And finally, last index of ai we update to I after we are done with this j loop. Okay, so hopefully this code is clear. This is the setters code. You can also see this in the editorial section. Yeah, not this one. Yeah. So this is the part where you can find the setter solution, exact same solution that I just discussed now. This reducing the, so slow solution was the n square k solution that we discussed. Reducing the transition is the optimization that we discussed using pref max and last. Okay. This slightly different approach we are not discussing right now. You can look through it. It's not very different. So I think we are done here. I'm glad you are trying this problem. You should try to implement and submit this. So yeah, hopefully you enjoyed this editorial, and bye.